Welcome back to the video lecture series on data communications and networking. Myself, Jasir MP, Assistant Professor, MES College, Marampalli. Today, we are going to discuss switching. Let's have a look at the trivial switched network shown in the diagram. Instead of establishing connections between each and every systems, we have implemented a number of switches in the network to provide temporary connections whenever needed. Now, switched networks are classified into three: circuit switch networks, packet switch networks, and message switch networks. Packet switch networks are further classified into two: datagram networks and virtual circuit networks. Now, circuit switch networks. A circuit switch network consists of a set of switches connected by physical links. A connection between two stations is a dedicated path made of one or more links. However, each connection uses only one dedicated channel on each link. Each link is normally divided into n channels by using frequency division multiplexing or time division multiplexing. So, the idea is to provide high bandwidth connections by using frequency division multiplexing or time division multiplexing to be utilized by low bandwidth systems. Providing high bandwidth connections realized using frequency division multiplexing or time division multiplexing to be utilized by individual low bandwidth systems. The topics discussed in this section are the three phases in circuit switch networks, efficiency, delay, and circuit switch technology in telephone networks. A circuit switch network is made of a set of switches connected by physical link in which each link is divided into n channels. Whenever two systems establish a connection, one of this n channel is reserved to that particular source and destination. A trivial circuit switch network is shown in the figure. System A is establishing a connection with system M, which is highlighted with the pink arrow. You can see that different systems are connected to a switch and different switches are connected via high bandwidth multiplex links. These links are shared between these different channels. At the destination, this high bandwidth channel is demultiplexed into individual channels and the data is redirected to the intended destinations. In circuit switching, the resources need to be reserved during the setup phase. The resources remain dedicated for the entire duration of data transfer until the teardown phase. Now, let's have a look at the delay in a circuit switch network. System A sends a connection request to System B. It reaches System B after some time and System B responds to it, and a connection is established between A and B. Once the connection is established, the resources are reserved and the data can be freely transferred in either directions. Once the data transfer is over, one of the parties can initiate a disconnect and tear down the resources. The figure shows once the connection is established, the data transfer can occur freely without any delay. Switching is happening at the physical layer, and traditional telephone network is a classical example of circuit switching approach. Datagram networks. In data communications, we need to send messages from one end system to another. If the message is going to pass through a packet switch network, it needs to be divided into packets of fixed or variable size. The size of the packet is determined by the network and the governing protocol. Topics discussed in this section are routing table, efficiency, delay, and datagram networks in the internet. In packet switch networks, there is no resource reservation. Resources are allocated on demand. Now let's have a look at a datagram network with four switches. System A is establishing a connection with System X. System A has to send four packets numbered 1, 2, 3, and 4 over the switched network. As you can see, the packets take any of the possible routes to reach the destination in any possible order. So, reordering the packets and delivering the packets to the intended process is the duty of the network protocols at the destination. There will be a routing table in a datagram network at every router as shown in the figure. The routing table will have different destination address and the output ports through which the data to be sent. For example, in this figure, destination address 1232 has to be routed through output port 1. Destination address 4150 has to be routed through output port 2. A switch in a datagram network uses a routing table that is based on the destination address. The destination address is in the header of a packet in a datagram network, and it remains the same during the entire journey of the packet. Now let's have a look at the delay in a datagram network. As you could imagine, no resources are reserved, so system A in this case transmits the packet. It reaches switch 1. At switch 1, the packet has to wait a particular amount of time to be served. After that time, the packet is forwarded to another switch or the destination. So at each intermediate switch, the packet spends some time in the input queue to be served. As a result of it, the delay in a datagram network is a bit higher compared to circuit switch networks. Switching in the internet is done by using the datagram approach to packet switching at the network layer. Now, virtual circuit networks. A virtual circuit network is a cross between a circuit switch network and a datagram network. It has some characteristics of both. Topics discussed in this section are addressing three phases, efficiency, and delay. Now, let's have a look at the virtual circuit network. Just like any switcher networks, the connections are established through switches and the temporary means of connection they provide. Now, in order to establish a virtual circuit network, we use a virtual circuit identifier. The virtual circuit identifier is nothing but a locally unique identifier in the scope of a local area network. So, any data packet that receives at a particular router as shown in figure will have a virtual circuit identifier along with it. This virtual circuit identifier represents the virtual circuit identifier represents the unique ID of the previous node or router which sent the packet to this router. Similarly, the router updates the virtual circuit identifier with the receiving router to which the router will be forwarding the packet. So, you can very well see a data packet reaches at the router with virtual circuit identifier 14, and the data packet leaves the router with an updated virtual circuit identifier 77, which represent the recipient of this data packet. So every router will have switch and table. So every router will have tables in a virtual circuit network as shown in the figure. There will be incoming port VCIs and outgoing port VCIs in the routing table. So as per this table, every incoming VCIs, as per this routing table, port 1 receives VCIs 14 and 77, and 14 is forwarded through port 3 with a VCI of 22, and 77 is forwarded through port 2 with 41. The figure shows the source to destination data transfer in a virtual circuit network. System A sends a data with a virtual circuit identifier 14, which is received at the router through port 1 and forwarded through port 3 with virtual circuit identifier 66, and switch 2 receives this data with the virtual circuit identifier 66 and forward it through port 2 with a VCI of 22. Similarly, switch 3 receives this data through port 2 and forward it through port 3 with VCI 77, which means a virtual circuit consisting of different routers with particular VCIs constitute the connection. Now let us see how a setup request is established in a virtual circuit network. Switch 1 receives a packet through port 1 with a virtual circuit identifier of 14, and it routes the packet through output port 3 without filling the VCI information because it doesn't know yet the receiving router's VCI, but it does know that the packet has to be routed through port 3 because it does know the destination address of B. Now at switch 2 receives the packet through port 1. It does know that it comes from the router with virtual circuit identifier 66, and it sends the packet through output port 2 without filling the recipient's VCI. At switch 3, same step repeats. It accepts the packet through port 2 with a virtual circuit identifier of 22 and forwards the packet without filling VCI. Now, The destination B receives the packet and B does know that its virtual circuit identifier is 77. B sends the acknowledgement back. The left out informations are completed as shown in the figure. Now this is how a setup acknowledgement is established in a virtual circuit network. So after the acknowledgement, you can see that every outgoing port is now filled. B sends the packet, acknowledgement packet back to switch 3. Now switch 3 does know that the packet comes from virtual circuit identifier 77. Similarly, switch 2 and switch 1 fill in the required information and all the entries in the table are complete. Now, as a result of it, a virtual circuit is established. Now, as a result, a virtual circuit is established between A and B with a number of routers with specific virtual circuit identifiers are participating. Now, the data can be freely transferred between A and B using this virtual circuit network. So, in virtual circuit networks, all packets belonging to the same source and destination travel the same path, but the packets may arrive at the destination with different delays if resource allocation is on demand. Now, the delay in a virtual circuit network is somewhat similar to circuit switch networks. A connection is set up. Once the connection is set up, the virtual circuit can be used with much lesser delay than compared to datagram network as shown in the figure. Still, it takes some time at each switches depending on the network scenario at that time. Now, this is how the delay diagram in a virtual circuit network looks like. After setting up a connection, the data can be transmitted, but it takes some time at intermediate switches depending on the data traffic and other characteristics, but still the delay is much lesser compared to datagram networks. And just like in circuit switch networks, the connection has to be established, data transfer has to be completed, and the connection has to be tiered down in 3 steps in virtual circuit networks also. Now switching is performed at the data link layer in a switched WAN. Now in this case the switching is performed, and in this case switching is performed in data link layer. Now message switching is just a case of packet switching where a message is routed entirely rather than subdividing the message into different packets. Structure of a switch. We use switches in circuit switch and packet switch networks. In this section, we discuss the structure of the switches used in each type of network. This is a crossbar switch. We have 3 inputs and 4 outputs, and a connection has to be established between each of these combinations. So we have 3 into 4, 12 cross points to establish the connection. The figure shows a multi-stage switch. This is to reduce the number of cross points. If we have n inputs, capital N, and n outputs, we need n square cross points. But if we rearrange each of the switches into 3 stages as shown in the figure, the number of cross points can be reduced to 2kn plus k into capital N by n square. So the idea of having multi-stage switches is to reduce the number of cross points. This is another case of switch, a Bunyan switch. Now consider the scenarios. Input 1 sending a cell to output 6. You know that output 6 is 110. So the input 1 has to activate the paths as shown by the pink line in the figure to realize a connection to output 6. Similarly, input 5 sending a cell to output 2. The highlighted path shows a connection is made from 5 through 0, 1 and 0, which is equivalent to 2. So this is how the routing is done using a Bunyan switching. In today's class, we discuss different switching methodologies: circuit switching, packet switching, and message switching. We also had a look at structure of switches. Thank you.